Okay guys, this morning we're going to take a look at the reaction of alkenes. And so the first thing we're going to look at is the structure of ethene, the simplest of all the alkenes, 2 carbon atoms and 4 hydrogen atoms. So first of all, what I'm going to do is to just colour in these various orbitals. So the s orbitals I'm going to colour in this orange, and as you hopefully know, the s orbitals are spherical in shape, and each hydrogen atom has its outer electrons in an s orbital, one s1. Then I'm going to go with a green, I think, on the sp2 orbitals, and these are these ones here, each carbon atom having 3 of these. Going back, this one in the plane of the paper, this one in the plane of the paper overlapping with that one, and this one coming at us, and this one going away from us. Okay, and the last one I'm going to colour in is the p orbital, and that one is yellow, if you can see that, and p orbital is a dumbbell shape, like this. Okay, now just going to pop the electrons in here. Now each of these orbitals has got 1 electron in them, so there's the p orbital electron, there's an sp2 electron there, there and there. So there are the 4 electrons from a carbon atom. If I do the same here, there, there and there, and each hydrogen, remember, has just 1 electron in its 1s orbital. So I'm going to put them there, hopefully you can see them, a bit dark I'm afraid. Okay, so if we read the blurb on here then, so the carbon-carbon and the carbon-hydrogen bonds are formed by the overlap of the sp2 hybrid orbitals, in this case here, with themselves and with an s orbital. Now this makes for a really strong overlap, and so when the 2 orbitals overlap like this, it gives us a nice strong bond, and we refer to it as a sigma covalent bond. So that would be a sigma, so with that one, and that one, and that one, and that one. And these are either 350 kilojoules per mole in strength for the carbon-carbon bond, or 420 kilojoules per mole for the carbon-hydrogen bond. Stronger here because the hydrogen is nice and small and it can snuggle up to the carbon atom here. Shorter the covalent bond, the stronger it tends to be. But even so, a sigma bond between 2 carbon atoms is still going to be a strong covalent bond, and it's not likely to break in a chemical reaction, and therefore it's going to stay intact. However, the more interesting of the bonds probably is this overlap between the 2 p orbitals. And so if I show this here, now this is a bit of a stretch to get 2 p orbitals like this to overlap with each other, and as a result of that, this is a much weaker bond. It's known as a pi bond, and it's about 100 kilojoules per mole weaker, look at 260 kilojoules per mole. Now, in an alkene, this is the bond that breaks when it reacts, and alkenes tend to react much better than alkanes do because of this weakness in its structure. Now, you'll often see it shown down here as well. Now, I don't want you to get thinking now that there's some sort of triple bond forming here. There isn't. If these electrons happen to be in this space instead of up here, then we would get the pi bond down here. It's either there or there. You don't have 3 bonds, you just have 2. Okay, so that's the general structure of an alkene. Now, if I was showing this in an exam, or if I was answering this in an exam, I probably wouldn't draw such a complicated structure as this. I probably would draw something a bit simpler. So I'd show the sigma bond there between the 2 carbon atoms. I'd show the hydrogen coming towards me here and here. I would probably show the hydrogen going away from me here, and then I would show the p orbitals like this, and I would label them as a p orbital. Probably show the electron in them, and then I would show them overlapping. And I would then call that a pi bond. In terms of geometry, this is all a very flat structure. 120 degree bond angle between the CH bonds and between the CH and the CC as well. And if you remember your VSCPR from earlier in the year, this is a trigonal planar arrangement. So I'd draw something like that probably rather than that. A little bit simpler to draw. Okay. If we go on then, test for an alkene. Now there are two ways in which you can test for an alkene. You can either use bromine water or potassium permanganate solution. Now bromine water is by far the simpler of the two to use here, and bromine water before you use it is an orange solution. Now you have done this test at GCSE but probably don't remember it now. If you take this orange solution and you add it to an alkene, it will become a colourless solution as the bromine reacts with the pi bond in the alkene. And that's a very easy way to detect the presence of a double bond just by adding bromine water and losing that colour. KMnO4 works in a similar way. Potassium permanganate is a very dark purple solution, and when it reacts with an alkene it will again become colourless, just like bromine will. Not such a common test for an alkene though. We hardly ever do this test, but we always do this. Bromine is a very easy and simple routine test for an alkene. Okay, so reacting alkenes then, we're first going to look at a hydrogenation reaction. And this is where we take hydrogen gas and react it with an alkene. Now in this case it's going to react with ethene, and ethene being the simplest of all the alkenes. And so essentially what happens here is that we are going to transform this alkene into an alkane. So this is what remains of the alkene. The double bond is no more, it's gone. But it now has two extra hydrogens on board. Sometimes an alkene is referred to as an unsaturated hydrocarbon, whereas an alkane is referred to as a saturated hydrocarbon. That's because it's got more hydrogens on board. We've added these two on here. I'll just colour code that for those of you who like to have everything nice and coloured. So there's the hydrogen, and there it is there, and there it is there. Now in order to do this, you are going to need to use catalyst. Hydrogen won't just leap on board, even though that pi bond is strong, is weak rather. The hydrogen bond is quite strong. HH bond is quite strong, and so we need to break that first, or at least weaken it, and you can do that with a catalyst like nickel or platinum. Now the catalyst is a solid, whereas these are gases, and so when the catalyst is in a different phase to the reactant, we refer to it as a heterogeneous catalyst. Okay, now this is an addition reaction, and this is what alkenes do. They add things across a double bond, hydrogen being one of the things we can add across this double bond. Another thing we can do with an alkene is we can polymerize them. We can get them to join together. And again, you did this at GCSE, known as addition polymerization. And if we take ethene, we can get it to polymerize at high pressure, 2000 atmospheres, and quite high temperatures. The double bond again is gone. Instead, the electrons in that double bond, these two electrons, go one to either side, because these are going to now join on to other ethene monomers. So we use these long brackets, we put an N there because we're never quite sure how many of these are going to join together. Start off with N numbers there, and that N is going to be pretty large, in the thousands. So what we end up with here is a massive alkane, much, much bigger than nature ever intended. The biggest alkane in crude oil, for instance, is about 50 or so carbon atoms in size. However, we can get up to thousands and thousands of carbon atoms in size here. Basically, we're making plastics. And if you vary the alkene, you'll vary the plastic. The alkene is known as the monomer, this is known as the polymer. So in this case, this was ethene. If I colour here for you. This was ethene. and this would be polyethene. And so if you have styrene as your monomer, say, you could make polystyrene. Or if you had vinyl chloride as your monomer, you'd make polyvinyl chloride, PVC. You can make lots of different types of plastics just by changing the monomer or the alkene. Right then, let's look at some mechanisms for reacting these alkenes. So the main mechanism for reacting an alkene is known as an electrophilic addition, and the simplest type is reacting it with bromine. So if we look at the symbol equation, we're going to react this ethene now with bromine. Essentially what we're going to do is this test. So the ethene adds the bromine on board, so nothing is lost. So C2H4 remains, but we're going to add these two bromines. It's very similar to what we've done here. We've added the two hydrogens, but we're going to add the two bromines instead. So the mechanism has two distinct steps. The first thing that has to happen to begin with is that our bromine has to develop a temporary dipole. Now, normally the electrons in a bromine molecule like this are evenly distributed, but for a split second, let's just assume that the electrons have decided to move over toward this end. So this will have a temporary dipole, delta minus, delta plus. That's not going to last a long time, but it's going to last long enough for the reaction to kick off. And so these weakly held pi electrons, very weak attraction or very weak overlap between these two p orbitals, easily broken, are going to move, and we show the start of our curly arrow here on the middle of the double bond, are going to move into the space between this carbon and this bromine. We're about to form a covalent bond here. But this bromine's thinking, hang on a minute, I've already got one bond, I can't form two, so it's going to have to lose the bond that it already has. So the electrons in that bond both move on to the bromine. So the result of all of that is our double bond is gone, the sigma bond is still there, but the pi bond is gone. Hydrogens at the end here have got nothing to do with anything, so they're staying as they were. These hydrogens I'm going to show going up and down here. And the bromine now is bonded onto that carbon. The bromine that was on the other end of the Br2 is now as a bromide ion because it took both electrons with it. It owned one of them, but it's also pinched the electron from here, so it's got an extra electron on board, hence the negative charge. There's this carbon here had one of these electrons in this pi bond, but both of those electrons have gone here. And so it's now an electron down on where it was, so it's going to have a positive charge. It's a carbocation. So that's our first step. So the temporary dipole in the bromine molecule causes it to behave as an electrophile. So this here now, this bromine, I'll just color code it for you. It's an electrophile. It's got a partially positive charge, and therefore it's pulling electrons towards it. It's an electrophile. That's why we call it an electrophilic addition. And there it is there. There's the other bromine. It was here. There it is there. And it's going to appear here now in the second stage. It's not going to take a rocket scientist to think, oh, there's a negative charge here, there's a positive charge here. Are they going to get it together? Yes, they are. Going to form a bond between these two in this space. And so we can show that. I can find my black pen where I put it. We can show that like this. So here's the right hand side of the molecule. And here's the left hand side. And there's the bromine. Okay. I'll just end up my colour coding. So there's the bromine that was already on the bond. That was our yellow one. That started everything off. That was our electrophile. It is still there. And here's my other bromine there. So, electrophilic addition. Now you can do the same thing with HBr. So I'm just going to sketch that through with you here now. So if we had HBr, HBr works even better than bromine, to be honest. So there's our ethene. HBr doesn't have a temporary dipole, it has a permanent dipole. The electrons are permanently nearer to this bromine because it's more electronegative. And so this hydrogen is permanently with a slightly positive charge, not a temporary one as we saw in our Br2. And because of that, this works a bit better. So the electrons are going to move over from the pi bond, and we're going to form our intermediate here. There it is. And this is our carbocation, and our Br minus, remember. Oh, forgot that. There's the electrons going to form the Br minus. And then we're going to get these two joining together to form our product. Okay, so put some color coding on this. There's our electrophile this time, and there it is there, and there. Ooh, sorry, mess. And here's our bromine, forms a bromide and attaches on. So what we've done here basically is add HBr across this double bond, and we've gone from an alkene to a halogenoalkane. Okay, now the next bit is going to involve same thing basically, HBr, but not with ethene, like we just showed you a second ago, HBr with ethene, but instead HBr with propene. Now this, you might think, well, what's the difference? It's the same thing, isn't it? Well, not quite, because propene is an unsymmetrical alkene. So there's a decision to be made here. Let me show you what I mean. So if I show you the delta plus and delta minus again, and then we bring our electrons in from our pi bond onto that hydrogen, and the HBr bond's going to break. Question is the hydrogen going to go onto here, or is it going to go onto here? Now with our ethene, it didn't make a difference. I showed it going onto this one, but it could have gone onto the left hand side when I give us the exact same product, because if you flip these two around, you've got the exact same product. You've still got bromoethane. However, there is a difference here. If the hydrogen goes onto this end, it'll give us a different product to if it goes onto this end. So let's explore that. So there's our hydrogen electrophile, and in this first case we've put it going onto the left hand side, and in the second case I've put it going onto the right hand side. And so both are theoretically possible. So if it goes on the left hand side, this carbon here feels a bit naked in terms of its electrons. It's a carbocation. If it goes onto the right hand side, then this carbon becomes a carbocation. Either way, the bromide, the Br minus that's formed, is going to join on to the carbocation, and we're going to get our product. So our product in this first one sees the bromine go on the right hand side of the double bond. Whereas, sorry, I don't know, I should have put that straight up. On this one, the bromine goes on the left hand side of the double bond. So essentially what we made here then is 2 bromopropane whereas here we've made 1 bromopropane. Now, question is, do you get a 50-50 mixture of both, or does one dominate over the other? Well, the answer is one definitely dominates over the other. This one dominates over this one. We get about 99% of this one and about 1% of this one. The reason being, this, if I show you, is a secondary carbocation. This, however, is known as a primary carbocation. Secondary carbocations are way more stable. Tertiary carbocations are better still. This is secondary because it's got 2 carbons next to it. This is primary because it's got 1. The more carbons you can get around the carbocation, the more stable it tends to be. Oh, shown it there. And so, as a result, because this is more stable, it's more likely to hang around for the bromide to attach itself. Because if this is less stable, it's probably going to go back to here and the bromide doesn't get a chance to attach. So you get this 2-bromopropane because secondary carbocations are more stable than primary carbocations. So that is the reason why you get 2-bromopropane over 1-bromopropane.